Benzene and bomb calorimetry. A very important aspect of chemistry is figuring out how energy will relate to given systems and particularly reactions. In this specific example, I'm going to talk about the relationship between the resonance energies of the compound benzene and how it can be experimentally determined using calorimetry, specifically by analyzing temperature versus time. Before going into how the experiment was conducted, it is very important to understand the methods that are going to be used in determining the answer to our given problem. The first method that needs to be understood is how to analyze a chemical equation and to how to understand what it can tell us. For this experiment, we have this equation showing benzene reacting with cyclohexene to produce CDDT in the top right of the slide. This is very important conceptually and mathematically to understand because it shows us what should happen if these given conditions were to be met. It also allows us to apply something called Hess's law. Hess's law allows us to create a relationship between this reaction and thermodynamic properties such as enthalpy. There are many different types of enthalpy, such as condensation, combustion, vaporization, and formation, all of which can be determined through relationships that are possible because of Hess's law. This relationship eventually also leads us to the resonance energy of a compound, which is exactly the solution we are looking for in this problem. Understanding the thermodynamics that must be used in this experiment is also immensely important. The first equation given here is used to determine the heat of a system by using the change in temperature represented by the delta T and the specific heat, which is labeled by the capital C. That equation is also adjusted to account for the energy created by the burning of the ignition wire, and this is represented on the right side of the equation by the Q sub W and Q sub WU for the starting and ending wire length, which corresponds to energy, respectively. The specific heats of the calorimeters were given, and everything else was experimentally determined. This heat was then used in the equation on the bottom along with a portion of the ideal gas law equation to determine the enthalpy of the corresponding reaction. After having a good grasp on the methodology and concepts of the experiment, it is time to move into how the experiment is going to be performed. The start of the procedure deals with making sure that the calorimeters, which can be pictured in the bottom right photo, are in good condition with being clean and making sure that all the pieces are in working order. After checking those steps, solutions can be prepared by either adding a certain volume of the CDDT to the dish or filling a capsule with the cyclohexane. It is very important to note that all relevant details, such as the mass of the samples and the mass of the capsules holding the cyclohexane. The next part is getting a correctly sized piece of ignition wire, which should be around 10 centimeters, and it is very important that the exact length is noted due to it having an effect on one of the previous equations when solving for the heat of the system. After cutting and measuring the wire, the calorimeter can be put together. During this step, it is very important that the top part is held upright the entire time so that the sample in the basket does not spill out. After putting the calorimeter on, you would then screw the locking mechanism onto the top of the calorimeter. Once everything is put together, the whole system is brought to the oxygen tank, where the calorimeter is then vented at least 3 times and then pressurized with oxygen to make sure that all other gas is purged from the system. After this, the jacket is prepped so the calorimeter can be placed inside of it and then filled with 2 liters of water. After filling the water, the ignition wires are then connected to the top of the capsule, and then the rest of the apparatus is secured using the lid and clamps. Once everything is secured and hooked up, the software should be opened and there should be a baseline temperature which would be recorded for at least a minute. After this time has passed, the system can be ignited and the data will be recorded until the temperature has a longer plateau. Once a plateau has been reached, the data collection can be stopped and should be exported for further analysis. Once the data is exported, it can be brought into Microsoft Excel and a graph of the temperature versus time can be created. This can be seen in the top left. It is good to note that on this graph, the time frame of the baseline temperature can be seen at the start, along with the longer plateau that was previously mentioned at the end. From this graph, points that are used to find the change of temperature can be determined and then used in the future equation. Also in this equation, the slope of certain parts of the shown graph are used for that same equation. The areas of interest were focused on, and their own graphs were created to determine their slope for values for further calculation, which can be seen in the graph on the right. The important values on the graph on the left are noted with arrows labeling points A on the left representing time of ignition, B in the middle of the graph representing 60% of total temperature, and C reaching the maximum temperature, which these values are used in the determination and change of temperature. After doing some initial analysis on the graphs, the next step is to do calculation to determine the change in temperature. So as previously stated, the points of interest from the graph were used in this equation for both their time and temperature values. On the right side of the equation, we can see that the R variables, and those are the slopes of the more focused graphs that were prior mentioned. Besides doing graph analysis, Cygress was also used to create the three molecules being benzene, cyclohexane, and CDDT from left to right on the bottom of the slide. The software also allowed us to find the enthalpy of formation values from using a built-in calculation feature, which are shown in a later table. Once the change in temperature was found for all of the trial runs, that data could then be plugged into the following equation along with the specific heat values that were given and the adjustment for the energy of the wire to determine the heat of the system. After determining the heat of the system, we can then plug that into another equation to determine the enthalpy of the reaction. However, that equation has a portion of the ideal gas law, which has a variable that represents change in moles. So that is the first part that needs to be determined, which can be solved for by using basic stoichiometry, which is shown at the bottom of this slide. After finding the change in moles, the rest of the equation is now known since we had previously solved for the heat. R represents the ideal gas constant, which is known to be 8.314, and the temperature is set to standard conditions, which is 298 Kelvin. Following the calculations, it is important to make sure that all the values obtained and used are kept in an orderly and easy to read manner. Because of this, multiple tables were created, and the first of which is this one, which includes what trial is being mentioned, along with all the values that were used in the determination of the change in temperature from the previous calculations. Then, Table 2 is created, and this contains the trials with the experimental masses along with their respective heats and then their enthalpies of combustion. After filling in this information, the data was taken from the Cygress software and put into Table 3. Another set of data was also obtained as literature values for the enthalpy of combustion and vaporization for benzene, along with the enthalpy of vaporization for cyclohexene. These values were obtained from the NIST database website, and they can be seen in Table 4. Table 5 is the final table that was created, and this follows the relationship of Hess's law that goes through the initial equation that eventually leads us to the determination of the resonance energy. Using this data, many conclusions can be made. One of the most prominent is the stability of and the amount of energy that is needed to change benzene into a different compound. A large factor of this is its conjugation. However, it can still be seen that it is much more stable than other compounds that also have strong conjugation. This is primarily because benzene is so aromatic, which is a way that it differs from the other compounds that it is often compared to. Another result that could be seen was the method of using Cygress showed to be the most accurate with the lowest discrepancies and therefore the lowest percent error value. I believe that this could be due to a number of factors, but I think the most prominent one is that it is being run by a software where there would have no human error factor or just random errors that could arise when doing an in-person experiment. Another piece to note is that one of the original hypotheses that were stated was shown to be true, that the energy of benzene was much higher than that of cyclohexane, mainly due to its conjugation and aromatic structure. I would like to recognize NIST as some of my sources for the data that was used in one of the tables, along with recognizing the lab manual for any help conceptually. Thank you.